Okay, quick summary of thinking on problem 5. The information we have is that if you have two tubes connected as shown here, and you invert the tubes in this direction, the water in the tubes will fill the lower tube to a depth of 4 centimeters. If you turn it around this way so that the thinner tube is lower, it's filled by the same amount of water to a depth of 9 centimeters. So we think, in the way the problem is stated, we have water being introduced into the larger tube, and it's rising at a certain rate, and when it gets up to here, it continues rising in the smaller tube. The same amount of volume is being introduced during every time interval. That is, the volume rate at which water is entering these tubes is the same in all circumstances. The question then is, if this arrow represents how fast water rises when in the wider tube, then, and this arrow represents how fast the water rises when it's in the narrower tube, should this arrow be longer or shorter than this arrow? And the correct answer to that is it's got to be longer, because 4 centimeters of depth here corresponds to the same volume as 9 centimeters of depth here. So whatever time takes to fill 4 centimeters here is going to fill 9 centimeters up here. The result is that water is going to rise 9/4 as fast in the thinner tube. So that if the speed in the wider tube is 3 centimeters per second, the speed in the narrow tube has to be 9/4 of that, which is 27/4 centimeters per second, 6.75 centimeters per second, and that's the answer to one of the questions. Now, a little more detail here. This just says what I said before. In the time it takes to fill this 4 centimeters, this will rise 9 centimeters. This note says, therefore the water rises 9 centimeters in the thinner tube in the same time required to rise 4 centimeters in the wider tube, so it rises 9/4 as fast as in the thinner tube. And then the answer to this intermediate question, which wasn't part of the problem, just a question I posed in trying to explain this problem, this should be 9/4 as long as this. Okay, the orange 9/4 as long as the yellow, because this represents how fast water's moving through the larger tube, this how fast water's moving through the smaller tube. Now, if you have two cylinders of the same volume, well, the next question is, how do the cross-sectional areas and the radii of the two tubes compare? Well, the volume of any cylinder is equal to its cross-sectional area times its height. So, if they have the same volume, but one has 9/4 of the altitude, then how do their cross-sectional areas compare? Well, ACS times H, cross-sectional area times height, which is equal to the volume, basic principle, when you have a uniform cross-sectional area, is the same for both, so the cross-sectional area of the narrower tube has to be 4/9 that of the wider tube. Because if the narrower tube has 9/4 of the altitude, to get the same volume, it's got to have 4/9 of the cross-sectional area. Now we'll do that more formally, but that should be something that you should, if that's not completely obvious to you, that's something you should think through until it is. Then, if, well, we've concluded that the cross-sectional area of the narrow tube is then 4/9 that of the larger, which means, of course, the cross-sectional area, these being round tubes, is given by, of either tube, is given by pi r squared for that tube. And then that's multiplied by h for that tube to get the volume. Now, people want to start with this formula of volume is pi r squared h rather than this principle, which is when you have a uniform cross-sectional area, the volume is cross-sectional area times altitude. This doesn't work just for circular cylinders. This only applies to circular cylinders. If you have a pentagonal cylinder or a square, or, well, pentagonal would be a prism or an elliptical cylinder, you wouldn't have pi r squared for the cross-sectional area, would you? So the reason you have this formula for a circular cylinder is simply the cross-sectional area of a circle is pi times the square of its radius. In any case, now, if pi r squared is 4/9 as great, which is the case for the thinner cylinder versus the thicker, pi r squared is 4/9 as great, then r squared has to be 4/9 as great. Pi is the same both times for both cylinders that we're comparing. It's only the r squared that determines the ratio of the cross-sectional areas. If r squared is 4/9 as great, then what's the ratio of r? What's the ratio of the radii? The squared radii are in ratio of 4/9. What's the ratio for the radii? Well, here we have a list of the things that we've reasoned out. For the same volume, the height of the narrow cylinder must be 9/4 that of the wider, so its cross-sectional area has to be 4/9, since the product of cross-sectional area and height has to be the same for both. So pi r squared for the narrower is 4/9 that of the wider. It follows that r squared for the narrower is 4/9 that of the wider, and it follows immediately from that that r is going to be square root of 4/9, or 2/3 that of the wider. Now, that's intuitive reasoning that's well-based and can be proven algebraically, and we did that over here. We say height of the narrow cylinder is 9/4 the height of the wide cylinder. Volume of the wide cylinder equals volume of the narrower cylinder. So we can write an equation. Cross-sectional area of the wider times the height of the wider is the volume of the wider, and cross-sectional area of the narrow for the height times the height of the narrow is the volume of the narrow cylinder. Thus, the ratio of the cross-sectional area, cross-sectional of the narrow divided by the cross-sectional of the wide, which is what we're trying to find down here, is equal to the height of the wide divided by the height of the narrow. Just algebraically rearrange this equation, and since the height of the narrow is 9/4 the height of the wider, then we replace that, we get this ratio. Height of the wider divides out, reciprocal of 9/4 is 4/9. So the area ratio of the areas is indeed 4/9. That means then, of course, since the area is pi r squared for this thing, pi times the radius of the narrow squared over pi times the radius of the wide squared is going to be the same as this. It's going to be 4/9. So that dividing out, the pi divides out, we get rn squared over rw squared equals 4/9. This rn squared over rw squared is a quantity, rn over rw squared. That's 4/9. Taking the square root of both sides, now officially we'd have to do plus or minus the square root of both sides to solve this equation, but we're not going to get a negative ratio, so we just kind of dismiss the minus before we go on. And we get square root of 4/9, of course, is 2/3, so rn over rw equals 2/3, and rn is 2/3 of rw. That is, the radius of the narrow cylinder is 2/3 the radius of the wider. Of course, the way I drew it, the wider was a lot more, the narrower was a lot less, let's say, than 2/3 the width of the wider, or the diameter of the wider. That was just for illustration. Okay, you could estimate the ratios as I drew them and see what you think the ratios would come out. That wouldn't be a bad exercise. In any case, this is how we can symbolically prove that our reasoning was correct, and we should always be able to do this reasoning, but we should always be able to symbolize it to prove it.